Hello class, this is Tim Tomlanovich. Welcome to Water Technology. We're on Learning Plan 7. We're talking about Chapter 3 of your textbook, Hydrology. Okay, so with that, let's start with the hydrologic cycle. So the hydrologic cycle, water is always in constant motion. Water is on the surface, lakes, streams, reservoirs. It's underneath the surface of the earth, groundwater, aquifers, and it's above the surface. So it's always moving. Okay, above the surface, it's water vapor. So it condenses when it gets high enough, and then precipitation falls back down. So a more of a term, a more technical term, transpiration. I don't know if you remember hearing this from your science class. Water absorbed by vegetation and released back into the atmosphere as a vapor. We have evaporation, which is basically sun, wind, temperature. Water levels in lakes will decrease if the precipitation rate does not exceed the evaporation rate. Water levels go down. And there's something called evapotranspiration. It's a combined process of evaporation and transpiration. Then there's an aquifer, water that fills the voids and fractures of bedrock and pore space between soil particles. And then base flow. Base flow is when groundwater, an aquifer, exits onto the surface of the earth. So there's always a base flow. Typically, we have to take into account due to groundwater when we're talking about watersheds and runoff. Okay, so on the right side here, you can see the diagram from your book. Basically, it's a continuous cycle. So what rain falls, it hits the plants and trees. Transpiration happens, it absorbs it in, and then it releases back into vapor, back into the atmosphere. And evaporation is direct evaporation that condenses, it falls back down. Anything that doesn't hit the plants, um, non-transpiration or evaporation, will hit the ground. It soaks into the ground, recharge our groundwater. Okay. All right, so let's talk about rainfall. So how do we measure rainfall depth? It's called a rain gauge. So as you can see in these pictures on the right, these are rain gauges, and the lower picture is a very heavy rain. This rainfall gauge that you see in the upper left, the orange one here, is reading 1.1 inches. That is total rainfall during that duration of that storm, total rainfall depth. Okay, we measure it in inches or millimeters. And typically what's reported in a weather station is average of several rain gauges around the viewing area. So when you look at your weather app. Let's talk about volume. Volume is a depth, a rainfall depth times an area, a surface area. So in metric, it's cubic meters. So remember, you got to do your unit conversion. You got to change the depth, rainfall depth from millimeters to meters and multiply it by square meters to get cubic meters. From sewer design, you see this term a hectare. When we have very large watersheds or areas, it's easier to work in hectares than square or cubic meters or square meters, and 1 hectare equals 10,000 square meters. In the US, we have cubic feet, and then we have an acre feet is a term. An acre feet is one surface area of acre. Area is equal to 1 acre. On the upper right-hand corner of this, you'll see a picture I took from the book. It can be a circle or a square. So 1 acre of surface area has a depth of 1 foot of water over the entire area. So they call that a 1 acre feet of water. Okay, so it's a larger unit because sometimes these calculations get so big because of the area. So volume is depth times area. Let's talk about intensity. Again, we have the rain gauges that will capture that rain through the duration of that rainfall. So to figure out intensity, typically we want to know how many inches per hour, millimeters per minute, or millimeters per hour. Okay, so basically you take the total rainfall and divide it by the duration, and I can get it in intensity. So in the upper left-hand corner here, it's something called a hydrograph. Basically, it's measuring the intensity of the rainfall versus the during time. Okay, so we can use that for our design. And then typically short duration storms, so those storms that come through here have higher average rainfall intensities and longer duration storms. So typically that's what we're seeing. Those storms, this next time it rains, observe how long it takes. So if how long it lasts, and typically those soakers, we call them those soaker rains, those 24-hour storms that last all day, their intensity really isn't that large, but the rainfall can accumulate, okay? Versus those storms that come in and last 10 minutes, those storm intensities are very high, okay? So it's kind of a pattern that we're seeing more short duration storms due to our Earth changing geologically and climate change. Reoccurrence interval. All right, time span or period between storms are not constant. Occurrence of rainfall, intensity, and duration are random natural events. So every single storm that happens typically is not repeated, okay, during a given year. So they're typically different. Every storm is different. The duration is different. The intensity is different. However, it may be repeated somewhere else down the line. Okay, so that's what we call a reoccurrence interval or a return period, they call it. So what we do, since they've been starting to record data of any rainfall event over time, basically they look statistically, they analyze it and say, okay, this specific intensity, number of inches per hour, rainfall intensity, and that specific duration has occurred the time between those same intensities and durations. So that's what they call an N-year storm. N is like 100-year storm. So a 100-year storm is the reoccurrence interval. A 5-year storm, 25-year storm, etc. Reoccurrence interval or return period, they sometimes call it. So it means over a long period of time, the average time span between storms of that particular intensity and duration. However, this does not mean a similar storm will occur once exactly 100 years for a 100-year storm. More than one of these 100-year storms could occur in any given year. So we could have one, we could have two, we may not even have any, okay? We could have three. So basically that's telling us over a span of 5 years based on statistical data, remember it's still random, you can expect 5 100-year storms. So that's that return period or reoccurrence interval. So it's related each. So a 100-year storm has a different intensity and duration versus a 5-year storm has a different intensity and duration. Okay, so that's how they categorize these storms. So now we got to determine what's the probability of occurrence of those storms. Okay, so again, using statistics, the probability or chance that a given event will occur can be expressed as a fraction, decimal, or percent. So basically, P, probability, is 1 divided by N. N is that reoccurrence interval. So if I take 1 divided by a 5-year storm, 1 divided by 5, there is a 20% probability of that event being equal or exceeded in any given year. So there's a 20% chance I am going to see a 5-year storm. Okay. Now, larger intervals usually have a lower probability. So a 100-year storm has a 1%. There's a 1% chance that you could see or exceed that storm. So it's probability. It doesn't mean it's going to happen. It's probability. Okay. Think about a quarter. There's heads and tails. There's two different options that can happen when you flip a quarter. 2 times. So if I take 1 over 2, there is a 50% probability that it's going to be heads or tails. Doesn't mean 50% of the flips are going to be heads and 50% are going to be tails. It's just the chance of being heads or tails. Okay, so something to keep that in mind. All right, so let's look at rainfall curves. So the relationship between rainfall intensity, duration, and frequency, IDF curves, intensity, duration, frequency curves, basically are developed for specific areas. So looking at different websites, and I found our IDF curve for Green Bay, Wisconsin, looking at, I think it's this website right here. So go ahead and look at that. You can find it for any area in the United States. Again, this is statistical data that they keep accumulating over years after years after years, and they create these IDF curves for civil engineers to do their design. So how do these work? So basically, if you look on the diagram on a basic general IDF curve on the right here, this is from your book. So basically, the x-axis has storm duration of in minutes, and then the rainfall intensity is the y-axis. So for an example, if I have a 60-year storm, or I'm sorry, a 60-minute storm, or a 60-minute duration storm, and it lasts, and it's a five-year storm interval, I come over, my rainfall intensity should be about 1.75 inches per hour. Now let's say I have a intensity of 5 inches per hour, okay, and that duration lasts 20 minutes. So I come up to 20 and I intersect there. So I'm between a 10 and a 25-year storm. Okay, so say it lasts 50 minutes. We're above a 100-year storm event. So as you go to the right, as you can see, the duration of these storms are less and less. Okay, so that's how you can interpolate that graph. Interpolate, yes. All right. There's also a rainfall classification. So we need to classify these rainstorms similar to earthquakes on the Richter scale, magnitudes. So if you look at the example here on the upper right-hand corner, this is the Haystack Severity Index levels from your book. On the x-axis is duration in hours. Y-axis is return period. So if you look, if I have a return period of a 10-year storm, which is the N value, okay, and a duration of 2 hours, I have a Haystack Severity Index level of just over 5. So now I come down to the table, 4 to 5.5. I'm in a category 2, and everything, and that's my category. Okay, so it gives you a category. So reason why this is important, because a 2-year 24-hour storm has a larger rainfall depth than a 50-year 1-hour storm. So remember, there's 3 pieces to the puzzle: intensity and duration, or 2 pieces: intensity and duration, okay, and return period. So yeah, 3 pieces of the puzzle. So just because you think it's a 100-year storm doesn't necessarily mean it's it's more damaging than a 5-year storm that's lasting, a duration is longer. Okay, so all right, so let's do our example here. Okay, and what I'm going to do is I'm going to go on to the whiteboard here. So during an 8-hour rainstorm event in Green Bay, 3.2 inches of rain fell over an area of 80 acres. Okay, we want to find all these answers. Compute the volume of rainfall, calculate the rainfall intensity, determine the reoccurrence interval, calculate the probability, and classify the storm. So what I recommend, I don't know if you heard about the Father's Day storm in 2018. These videos, I recommend watching these videos. They got 7 inches of rain in a period of 3 hours, something like that. That is extremely high storm. So I recommend looking at it. It's very interesting YouTube video, so you can see the damaging effects of of rain. So, all right, so let's solve this problem. Okay, so number one, okay, so we want to calculate the volume. 3.2 inches of rain times, we need to get that in feet, times 1 foot equals 12 inches. Okay, so and that equals 0.2667 feet. Okay, times 80 acres. Okay, what I'm going to do is I'm going to pause this video and continue with the lecture because my computer is acting goofy. So what I would like to do is finish this presentation and I'm going to create a separate video with this example, okay? So let me go back to that. Okay, so stay tuned for this example. And this is also attached in Blackboard. So we'll use these curves for that. So continuing on, surface water. Let's talk about surface water. Watersheds, drainage basin, or catchment area. Okay, terminology. Total land area that contributes to runoff to a stream or river. Large watersheds are also called river basins. Okay, drainage divide line, ridge line. Boundary of watershed, it separates adjacent watersheds. Point of confluence, point to which two streams converge or intersect. Subbasin, a smaller part of a larger watershed, and then tributary, smaller stream flowing into a larger stream. Okay, so if we look at this diagram on the right side, which is out of your book, it's showing a watershed. So we have a subbasin, okay, and if you look here, we have this river here. So if I go to slideshow from, oops, I'm going to just escape out of that. So if we have this tributary right here, okay? So basically a ridge line is basically, when you look at a contour map, is which way does the water flow when it hits the land? Does it go to this tributary or does it go this way? Okay, so they have something called first order streams. So first order streams don't have any other streams or tributaries into it. So if you look here, when water hits the land here, the water flows here, the water flows here, and it keeps going. Okay, and now the second order streams are right here. So here's another tributary. And basically what we figure out, this is the entire perimeter of the watershed right there. Okay, and then this is the outlet. So basically what we need to do, figure out a subbasin. Point of confluence is right there. So we want to figure out what's the flow there, and then the flow continues, because the step to watersheds is one, okay, let's do our divide line, and your book does a good job of this, explaining this. Let's figure out which way that water is going to run and which stream that water runs to, or manhole, etc. First, that's the first thing you figure out. Once you figure out that volume of flow going to that river, then you can calculate a flow going down the stream until where you need to figure out, the total flow, because we got the sheet flow and then we got all of this coming down. So at the end, just like sanitary sewer design, all of this flow, the flow gets bigger and bigger and bigger as it gets down to the outlet. Okay. So stream flow. We use Manning's equation. You know what Manning's equation is. It's open channel flow, stream flow. So we use cubic meters per second, cubic meters per hour, or million gallons per day. In US, we use cubic feet per second, okay? Acre feet per day, gallons per minute, million gallons per day. So Manning's equation. We know a slope, we know a roughness coefficient. We can figure out our flow based on the volume of flow here. So, okay, based on our set. So, a reach, another term, a section of stream that has a relatively constant slope, cross section, and discharge. So that's a reach. So if I look at the picture on the left, which is a stream, if this slope is constant and the geometry is constant, we can call that a reach. So in a detailed analysis to figure out how much flow is coming down to my outlet, basically we may have to modify, geometry, and that's where computer models come in handy. Okay. So stream flow, just similar to the hydrograph, but basically we call it a hydrograph. So basically discharge, Q, this is what we need to find, Q versus time. So here's that base flow term again. So there's that base flow. This stream has a base flow. So when it rains, it takes time for that water to, once it hits the river, it takes time for the water to build up and then to dissipate. They go through the system from point A to point B. So basically, this is what we need to figure out. This is called lag time. So as soon as that water hits the stream, how much time does it take to get to a maximum discharge before it starts depleting off? Okay, so this is the Qmax term that we need to design for. So they call that lag time. Okay, so that's another terminology. So with that, that is it for this presentation. I will show the sample calculation in a separate video. So thank you for your attention.